All right, welcome to the latest Advanced High Strength Steel Insights blog. I want to start off. Material testing has been around for a long time, and as long as the materials have been used, people have been interested in measuring how they behave, whether that's measuring the purity of copper in trade, elasticity of bowstrings, or even the strength of railroad tracks. We as humans have always taken a deep interest in understanding the properties of the materials that we use. What's interesting is that the latter example of these was actually what gave birth to ASTM in the late 1800s. As the number of specialized materials continued to grow, so too did our need to differentiate and characterize them. One of the ways that we do differentiate these is by their strength, both in slow and dynamic load applications. This video is going to go over a few examples of time-based events, then briefly discuss a case study on how the tensile strength of HSLA steel can vary with respect to strain rate. And then we're going to conclude by looking at a few different test methods that are available for dynamic material characterizations. I do want to say this blog and others are featured on AHSS leading online resource for technical information on the forming, joining, metallurgy of advanced high-strength steels for automotive applications. This information is made available by World Auto Steel, the automotive group of the World Steel Association. With that, I do want to say my name is Trey Leonard. I'm the owner and CEO of Standard Mechanics, a mechanical testing lab specializing in characterizing materials for formability, crashworthiness, and quality assurance. Got to start by saying something very simple. Things break. From car crashes to dropped phones, the products that we use every day deform and break from loads they experience. Along with that, each of these products is rigorously tested under similar loading scenarios to better predict how the product will perform. This could be to ensure compliance with industry standards such as the UL 962, which helps ensure safe office furniture. Alternatively, the test could be to quantify the resistance of damage or injury with industry standards like NHTSA. Many of the previous tests fall under the category of component level testing, though. Component level testing often emulates expected loading conditions on components or assemblies. A common example of this would be, say, a stamping trial. Conversely, coupon level testing loads material specimens in a controlled fashion to best understand the material's behavior with well-defined boundary conditions. A very common example of this would be the routine tensile test. Component level testing often includes higher costs, longer timelines, but they provide the most applicable results. Coupon level testing, conversely, is more cost effective and time efficient, but they often don't have a one-to-one relation to application. Now, the link between these two types of tests is where the world of simulations and digital twinning has emerged. A large goal of simulation is to use coupon level test results to accurately predict component level test results. There are many boundary conditions to take into account when performing coupon level tests, such as loading condition, direction, environment, temperature, etc. But one of the ones that is most often overlooked is time or speed. Looking at loading events, we see that the vast majority of these events occur on a timescale between a second and a millisecond. These are just a few examples that I have on the screen. There's obviously many more as we try to imagine what different loading conditions can happen around us. But very few events ramp up their loads over minutes, hours, or days, which starts with the balloon and the braces going into the scale of earthquakes and tectonic plates shifting. But even fewer events occur on the time scale of microseconds and nanoseconds. So on the other extreme, this is kind of in the ballistics or quantum realm. Even knowing that most components will experience these sub-second to millisecond loading conditions in their life cycle, the vast majority of coupon level testing occurs on timescales at least 100 to 1,000 times slower. We further define this boundary condition of time or speed as a rate of applied strain, also known as strain rate. Its unit is therefore strain per second, or simply called per second, but it's not to be confused with the frequency unit of hertz. Now, this is where we see the biggest problem. The standardized testing, like I said, is right around a minute. and it usually takes multiple minutes. Yet when we talk about these tests, we see how different that rate is compared to the rest of these events. So here's an example of how some strain rates can affect a mechanical property. In this case, we're going to be looking at tensile strength. Like I said in the beginning, this is just a typical HSLA grade of steel. So these are realistic tensile strength results from experiments across many different speeds. You can see that the x-axis is on a log scale, which is typical when looking at strain rate effects. Typical tension testing standards require testing speeds on the order of 10 to the minus 4 to 10 to the minus 3 per second. The load frames that perform these very tests can also be run at higher speeds. And if we do that, we can cover strain rates up to around 10 to the minus 1 per second. The problem is that strain rates occurring during a forming process are up to 10 to the 0 to 10 to the first. And then as we go into crash, we're even all the way up to 10 to the third. So dynamical tests are relatively more expensive than standardized lower strain rate tests. So a natural question to ask is, well, could we extrapolate to higher strain rates? In general, the answer to this is no, at least not consistently well. This is because many steels have an increase in strain rate sensitivity at around 10 to the 0 per second. Two common models used with strain rate sensitivity are the Johnson-Cook model as well as the Cowper-Symonds model. If we fit the lower strain rate data to these models, we can see that the agreement above 10 to the minus 1 or 10 to the 0, 10 to the 1, somewhere around that realm, drops off really quickly, with both models drastically misrepresenting the material's strength at strain rates present in crashes. For completeness, we can also look at extrapolation from the highest strain rates down, and we can see that that also doesn't present a good experience and a good model fit. The best model fit that we can do, the best alignment, obviously occurs when we use data from all the strain rates. So when we incorporate all of the data into the curve fit, we see the best alignment. The Johnson-Cook model still doesn't have the best alignment just simply due to its form. So another approach that can be taken is a split modeling approach, where you can take the data from lower strain rate tests to model lower strain rate phenomena and vice versa. So the final question we want to talk about is, if it's important, how is it that we actually get this high strain rate data? The method that many use are impact testers. This could be drop towers. This could be weighted pendulums. These are generally very adaptable test methods that can be changed and modified to different test configurations, different loading conditions, and they can handle a large variety of special geometries, sizes, shapes, and they also have very relatively low maintenance needs. Another common method for dynamic testing is using specialized servo-hydraulic load frames. These typically have higher throughput valves with larger accumulators and flow rates compared to the traditional fatigue load frames that we've often used, like I said, specifically in fatigue testing. All of these changes work together with mass trimming in certain areas to maximize the accelerations and speeds that this technology can achieve. The final test method is split Hopkinson pressure bar testing. These systems are often just called Hopkinson bars or Kolsky bars. This technique uses extremely low mass instrumented rods to achieve the highest velocities and strain rates. Hopkinson bars can easily achieve test velocities over 100 meters per second. So that wraps up this video blog. Visit www.ahssinsights.org to learn more about advanced high-strength steels. I want to say, finally, I'm Trey Leonard with Standard Mechanics. To learn more about the mechanical testing services we provide relative to material characterization or material card development, please visit us at standardmechanics.com. Thank you for watching and have a great day.